not so this long time ago at UT Austin, where his advisor was this nice person who unfortunately we don't see so well because of the projector quality, but is David Zuckerman. He then was a postdoc at the Institute of Advanced Study in Princeton for 2 years, and as of this fall, he's a faculty member at BCS, and as of very, very recently, he's also a CAM faculty appointments faculty member or field member. The particular work that he's talking about is, at least in part, I don't know if it's a full yet at all, won the Best Paper Award at Stock, so that's a very impressive piece of work. Best Paper Award here translates as they pick 1 or 2 papers that really are amazingly outstanding, and an otherwise very selective conference, and this is it. So you get to hear him explain something that was an amazing breakthrough in a research area that actually had an infancy when I started as a postdoc. And you can guess how old I am after Eshan will explain the beginning. So I let Eshan speak.
Thanks for coming here and thanks for this extremely fascinating introduction, Eva. Alright, so today I'll talk about some things called as extractors and another thing called as Ramsey graphs. So extractors arise in computer science, Ramsey graphs in combinatorics and mathematics, and how these two are related. And some motivation about how these things, why do we care about these things, and some explicit constructions of these objects. And this is joint work with David Zuckerman. So I'll start from the extractor point of view. So extractors come up in computation or in computer science when we think about using randomness in computation. Well, why do we care about randomness in computation? Well, I want to convince you that it's widely used in a bunch of areas. It's used in algorithms, it's used in cryptography, distributed computing, sampling problems. It's basically all over. I'm sure some of you have, or all of you have seen some randomized algorithm or a neat cryptographic protocol, or you must have used it for your own sampling problems. One example of use of randomness where we intrinsically need it is in cryptography. It's very crucial that the secret keys that you're using are actually random to the adversary, so the adversary should not have any information of what the secret key probably looks like. And for many protocols, which are widely used for say credit card transactions and other things, there are easy attacks known even if you know some structure about the key. And there's actually research which shows that if you think your distribution is random enough in some sense, then you might want to use it. And even basic cryptographic tasks like bit commitments and other things, they break down. Right? So cryptography is one area where you cannot do away with removing randomness. But another widely used place of random bits in computer science is randomized algorithms. An example is random sampling, where you have some complex quantity, say you want to estimate the solution space of polynomial equations, high degree equations, or volumes of weird objects. So the best, sometimes the best thing that you can do is just randomly sample, see how many of them fall in your set that you're trying to estimate, and get some approximation algorithms for these things, right? And there are various approximation algorithms. If you pick up a book on randomized algorithms, you'll find various really simple algorithms which are randomized, and probably we do not even know how to come up with a deterministic algorithm for these problems. And one example which kind of is a central problem in theoretical computer science is this problem of polynomial identity testing. It's fundamental because various problems can be formulated to be just doing this, checking whether given a polynomial, a multivariate polynomial on n variables over a large field f, decide if this polynomial is syntactically the zero polynomial, right? Or equivalently, given two polynomials, you want to check if they are both the same polynomial, if p is equal to q, right? And why is this a hard problem? Well, how are you given this polynomial, right? you're probably given it as a formula or a circuit. What this means is, you can think of the formula as like a product of sums, right? And the sum is over variables. So it's a circuit, and so your polynomial could be given as, say, a summation over product of linear terms, right? So what's the main algorithm for this? When given any succinct representation of a polynomial, you could expand it out, compute the coefficients of every monomial, and see if it's zero, right, over the field. But how much time does it take? So there are n choose d monomials. So it will take you something which is exponential in the degree of the polynomial. And if this polynomial, if the degree is set 0.1n, right, then this is an exponential time algorithm. And then here's a very simple randomized algorithm which works in polynomial time. Just pick a random x in your field and check if the polynomial is evaluates to 0 at this point. Right? If it evaluates to 0, you say yes, else you reject. And why is this true? Well, there's this really neat lemma, Schwarz-Zippel-Demino-Lipton lemma, or some of you know it as a Schwarz-Zippel lemma, which says that a low-degree polynomial, a low-degree multivariate polynomial has few roots. Right? It's just the extension of the univariate polynomial case. And it's a major open question if there's an efficient deterministic procedure, so efficient meaning poly n, poly d, an algorithm which actually does this. Right? So this is an example of a question where you have a simple polynomial n algorithm which is randomized, but you do not have a deterministic algorithm. We do not know if there is a deterministic. So the question is randomness required? Well, in randomized algorithms, it's not clear at all. It's probably that we are not smart enough right now. So a major conjecture here is actually showing that if you have a randomized, efficient randomized algorithm, so a randomized algorithm which works in poly n time, where n is the size of the input, then the conjecture says that you have an efficient deterministic algorithm for the same problem. And the conjecture is just based on our experience, right? So for, say, primality testing, there was a randomized algorithm known, say, 30 or 40 years back. And it took quite a while, but we eventually found in a breakthrough result by Agarwal, Dayal, and Saxena, we have a deterministic algorithm for primality testing. Primality testing, you're given an integer n to say if it's a prime. But in cryptography, we know that randomness is intrinsically required, right? And there are other areas like distributed computing and other applications where randomness is required. Right? So this is the state of our understanding of the use of randomness in computation. So now that probably I've convinced you that if you need randomness in computation, where do we get randomness from? Well, we could use some software solutions like, how operating systems schedule various tasks, or look at a specific user and see a typing pattern and look at the third digit of, the intervals between timings of typing, some ad hoc sources, or we could do slightly better and use some physical sources of randomness, like some quantum related phenomena, or look at electric circuits, or there's this really nice thing, clock drift, which maybe you can Google and see what this is, but it's a really nice thing. So what is typically seen is that you get a stream of bits which are random-like, but it's not at all clear that they are independent random bits, and each random bit is with probability half 0 with probability half 1. And typically applications, in the randomized algorithms that you analyze or in cryptography, you really require independent bits. So there's a bridge between what we have and what we need. And usually what happens in practice is you apply a complex looking function and you have no guarantee actually that it's actually uniform. So this is where randomness extractors come in, and a very high-level definition is it's a deterministic algorithm, right? So it gets a sample from a distribution which has some entropy, which we'll call a defective source, assuming that it's, and so it's an algorithm which gets a sample from a distribution with some entropy, and the goal is to output a few purely random bits, or the number of random bits should be equal to the entropy, close to the entropy of the source, right? So we'll make all these things formal. And the picture you should have in your head is there's this unknown distribution X. All we know about X is that it has some amount of entropy in it. We get a sample from this distribution in this function extractor. So for the purpose of this talk, we'll be really less ambitious and we'll just try to output one uniform. But usually there are techniques in pseudo-randomness and these things where if you can do something, then we can, get most of the entropy out. This is, yeah. So let's try to just get one uniform bit for this talk. All right. So now let's try to make things slightly more formal. Before that, let's try a simpler problem. Let's try to extract from a simple model of weak random sources. Suppose you get a stream of bits. Each of them are p-biased, right? So the probability that a bit is 0 is p, the probability that it's 1 is 1 minus p. And you do not know p, so p is an unknown, right? But p is fixed for each bit, and these bits are independent. Can you come up with an extractor for this random model of this source? So it turns out von Neumann was way ahead of his time, and he's thought of this problem in the 1950s. And I'll spoil the fun. So here is a simple extractor for this, which is just look at the stream of bits, pair them up. If the pair is 0, 1, you output. So you just output the first bit. So if it's 0, 1, you output 0. If it's 1, 0, you output 1. If both the bits are the same, either 0, 0 or 1, 1, you repeat. You can show that if p is bounded away from 0 or 1, right, then you do not have to repeat too many times, and the bit that you output is close to you. So, and this.
Sorry, it's uniform. Exactly uniform. Why was the uniform?
Right. Let's see. Yeah.
I mean, unless you cut it off and it didn't happen long enough, then you just was in
Right. Yeah, that's the idea. Right. So that's what.
Can you repeat the question?
I asked why is it not exactly uniform? This is exactly uniform. And I guess the answer is that if you don't want to wait indefinitely with even a tiny probability, you can change it. If you do this 100 times and if it always came out the same, then you output 1. And then it's almost uniform. With the small probability, it's an output.
Can you say anything about optimality of doing this?
You mean the number of times? The number of samples? I've not thought about it.
For p equals 1/4, you need about 4.5 bits of p point to get 1 bit of fair.
Obviously.
It's a calculation, just enter the calculation. So it's not optimal.
Do you know?
You can get arbitrarily close with a different line state machine.
That's good.
Yeah, it was if you knew P.
That's good.
If you know p.
So if you don't know P, maybe you can send me a proof. Okay. And this was generalized to Markov chains. It's a slightly more general model which was studied by Plum in the 80s. So the model of weak source that we'll be working with is motivated by entropy of the source. So I guess everyone's favorite definition is Shannon entropy, but unfortunately it's a weak assumption on the source in this setting. And here is a problematic distribution. Think of this distribution D, which is always the all zero string with very high probability, with probability 0.99, and with probability 0.01, it's uniform on n bits, right? So if you have worked with Shannon entropy for a bit, you can see that the Shannon entropy of this is actually linear in n. But if you just get one sample from X and you're trying to extract randomness, it's impossible, because without, you'll always see the all zero string. So the definition we'll be working with is min entropy of the source, which is the following: that you look at the maximum probability that your distribution places on its support, right? Then you take log 1 over that quantity. Right, so it's the worst case version of Shannon entropy. And if this looks like a slightly weird definition, let's go to the next slide to see how we should think about min entropy. And a quick note that the min entropy of this distribution T is actually order 1, because at this all zero string it places 0.99 probability, right? That's the max probability. So the min entropy is log of 1 over 0.99.
So if you look at some other order of spreading entropy, is it possible to do it? Like anything more than 1?
Right, that's a good question.
So if it's slightly more than 1, 2 or...
Right, so 2 is actually, it works nicely. So you can prove that, so it's pretty close to min entropy. It's like order constants here. Right, so we'll talk about n, k sources, which is, so source and distribution will mean the same in this talk. So it's a distribution of source on n bits, and it has min entropy at least k. So that's an n, k source. And what this means is that from the previous definition, that this distribution or source assumes any value with probability at most 2 to the minus k, right? So it does not assume any string with very high probability. Right? So there is some amount of uncertainty in this distribution, which is captured by min entropy. And a special case is to think of this n, k source as being uniform on some unknown subset of n-bit strings, and the size or cardinality of this subset is 2 to the k, 2 power k. Right? So it assumes every element in the subset with the same probability, which is 1 by 2 to the k. Clearly from the definition, it's a min entropy k source. And there is a lemma or a theorem by Shore and Goldrick from the 80s, which says that for most purposes, it's actually enough to just think of this extreme case, where your distribution is actually uniform on some subset of size 2 to the k. Right? So the model to keep in head for an n, k source is a distribution on some unknown subset of size 2 power k. Alright, so now that we have this nice notion of extractors and entropy, let's try to probably build a one source extractor. So what we want to do is X is some n, k source, where k, so clearly k is at most n, right? Because it's on 2 to the n elements. And we want to extract almost one uniform bit, right? A bit which is close to uniform. Well, there is a bad news here, that you cannot design an extractor which works for an n, n-1 source, right? So clearly, the maximum amount of min entropy is n, and this lemma is kind of saying that even if your source has efficiency of 1, then there cannot exist an extractor. So one thing to keep in mind is you're designing the extractor that works for every n, k source, right? You don't look at an n, k source and say, hey, here is an extractor for it. So the extractor should work for every n, k source. And the claim And the lemma here is saying that there cannot exist a single extractor for all n comma n minus 1 sources. This kind of bad news. And here is a simple proof of this fact. Well, let's assume such an extractor. Well, what's an extractor? It just maps n bit strings to either 0 or 1, right? It's a deterministic function. So here's a bunch of strings on which the extractor outputs 0, and here's a bunch of strings on which the extractor outputs 1. Is this clear? It's just a Boolean function. So at least one of these sets is of size 2 to the n minus 1. And now you define your distribution to be uniform on the larger set, right? So it's a uniform distribution on a set of size at least 2 power n minus 1. So it has entropy at least n minus 1, right? But your extractor either outputs always 0 or 1. It's nowhere close to, outputting a uniform vector, given a sample from the source, right? So, well, this was observed back in the 80s, and then people said they need more assumptions. But what we have access to more than one independent source. Suppose I give you two sources, X and Y. They're independent, and each of them has some entropy. That's one direction. The other direction said, well, if I give you, say, log n bits which are uniform and independent from the source that you're trying to extract from, can you use this helper seed to extract randomness out of your source? Right? So these things are called as seeded extractors. And the third direction was to say, make assumption on the single source that you have. It's an n comma k source, so it has some entropy, and also make some other assumption, like, for example, this source is the output of some sampling algorithm which has limited space, say. Or it's an n comma k source, and it's also known that this distribution is uniform on some affine subspace of f2 to the n. Right? Some assumption. Or just think of this simple case where it's a distribution on n bits, and you know that there are k unknown coordinates where each of these bits are uniform and independent, right? And the rest of the bits are, say, fixed to some values, right? So that's a bit fixing source. I mean, if you knew the location of one of these coordinates, you could just output that and you get a uniform bit. But so these are some sources which people have looked at. And so
Even if you don't know the source, or how to get that sort of everything?
you can just, yeah, that's a parity. But suppose you want to get like all of them 0.99k, then you have to do something. And in harder cases, if the fixed bits actually depend on the values of the alright, so this is a slide which we choose to ignore, but the message is that extractors are useful. So there has been a lot of research on constructing seeded extractors where you take a helper seed, and they have been used in inapproximability or hardness of approximation, which is a major area in computer science, in coding theory, where you want to send messages over, transmit messages over noisy channels, in constructions of expander graphs, which are useful and used in a bunch of areas. This simple model of bit fixing extractors have found applications in proving lower bounds, in complexity theory, and in cryptography. And affine extractors where your source has entropy k and it's uniform on some unknown subspace of dimension k, actually gives you the best known circuit lower bounds. So it's explicitly constructing extractors are useful, that's the message. And this talk will be about independent source extractors or two-source extractors. And these have applications in external combinatorics, which we'll see, and in distributed computing. And the general goal here is the following: that construct extractors for classes of distributions, making minimal assumptions on the source, right? So either you want to reduce the amount of complexity assumptions you are making on a single source, reduce the number of independent sources you're using, and also reduce the amount of entropy that you're assuming on the source. And finally, explicitly constructing such extractors is part of a bigger project in complexity theory. Constructing such objects with random-like properties is a central theme in complexity theory. So by random-like I mean, so a random object satisfies certain combinatorial, strong combinatorial properties or desired properties, and often you want to match, you pick up some combinatorial property of a random object and you want a deterministic, explicit construction of an object which enjoys this property. And there are generic ways of using such random-like objects to reduce the randomness in algorithms. And maybe the final goal here, after maybe 30 or 40 years, is to prove that you can actually de-randomize every randomized algorithm. And some other examples of such pseudo-random objects are expander graphs. So these are extremely sparse graphs, but are extremely well connected. So each set in this graph has a large expansion, either in terms of the neighbors it has or the number of outgoing edges. And random graphs are expanders, are extremely good expanders. So explicitly constructing expanders go a long way in a lot of applications. Pseudo-random generators, so these are objects which take in a short amount of randomness, expands it out into a larger string, and this larger string should look uniform to some complexity model, right? So again, a random function is a good pseudo-random generator. And finally, error-correcting codes, which are used, for transmitting messages. So a random function, if you pick it, it's a good error-correcting code, and constructing them has a lot of applications. So, and existence of each of them is proved by this really powerful method called the probabilistic method, which was introduced by Paul Parrish. All right, so let's get back to two-source extractors now. So the setting is the following. We have two sources, X and Y. They're independent. Each of them are on n bits. They're distributions. And the extractor gets a sample from X, a sample from Y, and all it has to do is output one bit. And what you want is that for any such two sources, the probability that the output of the extractor is 1 is close to 1 half. Right? So the probability that it outputs 0 is also close to 1 half. And this parameter epsilon is called the error of the extractor. Well, do we even know two-source extractors exist? It turns out that a random function is a good two-source extractor for entropy as small as log n plus order 1. Right? So both the sources are on n bits, but they just need to have entropy log n for an extractor to exist. So this is good news because one-source extractors do not exist. And if you just naively, go over all functions to see which is a good two-source extractor, it will take you a lot of time. Explicit constructions. That's what we are interested in computer science. And here's a matrix view of two-source extractors. It's the following. So capital N is 2 to the n, so this denotes the number of strings. Capital K is 2 to the k, which you can think of as the support of the distributions x and y, right? So each x and y have entropy k, so it's supported on some, you can think of it as being supported on some subset of size capital K. So constructing a two-source extractor is equivalent to filling up this matrix, this capital N cross capital N matrix, such that if you look at any capital K cross capital K submatrix, then the number of zeros and number of ones that you see are close to each other, right? So if you measure the discrepancy of a submatrix as being the number of zeros minus number of ones divided by the total number of entries, that corresponds to the error of your two-source extractor. Okay, so Alright, so this is the matrix view. And now I'll take a detour into Ramsey theory. So here's a picture of Frank P. Ramsey. We'll introduce this really nice, beautiful area of combinatorics, which studies the unavoidable presence of local structures in large objects, right? So it kind of says that if your object or your system is large enough, it must have some tiny amount of order in it. So making this more concrete, let's look at Ramsey graphs. So a Ramsey graph, it's an undirected graph on n vertices, such that it does not contain any clique or independent set of size k. So a clique of size k is a set of vertices of size k such that each of them are connected to each other, and an independent set is when all the edges are missing. And Ramsey in 1930 showed this theorem which falls in this Ramsey theory kind of theorems. It says that every graph on, so this should be capital N. Every graph on capital N vertices should either contain an independent set or clique of size log n over 2. Right? So it kind of says that, so this is the order being, that there is this clique or independent set. Right? And now Paul Erdős comes into the picture. He uses his probabilistic technique and shows that a random graph with high probability is a k-Ramsey graph with k being 2 log n, right? So Ramsey said that every graph on n vertices contains either a clique or independent set of size log n over 2. And Erdős showed that there are graphs on n vertices which neither has an independent set or clique of size k. So clearly if it does not have an independent set or clique of size k, it does not have something which is larger. And this is one of the first applications of this probabilistic method. And for completeness, let's look at a quick proof of this. And this is a handwritten proof. So, I mean, it's a basic exercise. What do? You pick a random GN half graph. So each edge is present with probability half and is missing with probability half. So for any subset of vertices S of size K, what's the probability that it's either a clique or an independent set? So it's a clique with this probability or it's an independent set with this probability, right? All the edges being present or missing. Let's twice this, and this denotes the number of sets of size K. As long as this quantity is bounded is less than 1. So this denotes the probability that there exists such a thing, and by union bound, this is less than 1, it means that with non-negligible probability, the graph does not contain an independent set or clique of size k. And if you pick k to be 2 log n, you see this is roughly n to the log n then, n power log n, and this is 2 power minus log square n, so it's n power log n. And you just, so 2 is very tight, you cannot go below 2 using this. Alright. And again, Ramsey, Paul Erdős said, can you come up with explicit constructions of Ramsey graphs? And if you do not think it's a neat problem, then he offered $100 to motivate you to solve this. And here's the connection between Ramsey graphs and 2-source extractors. Well, think of your first source as being on this, your second source as being on this. So there are capital N nodes on the left, capital N nodes on the right. Each node corresponds to a Boolean string of length n, little n. And suppose you are given a 2-source extractor that works for min entropy little k. So what do? So think of the complete graph being present, and you're coloring in edges either to green or orange or red. So you color it to green if the extractor outputs 1 on input A and B, and red if the extractor outputs 0. And the guarantee that the extractor has is that if you look at any source supported on capital K vertices here, any source supported on capital K vertices here. You pick a random guy here, a random node here, a random node here. The probability that there's going to be an edge is close to 1/2, right? So the number of edges between these two subsets of size capital K is roughly K square over 2, right? And Ramsey just wanted, Ramsey graph is defined where you do not want to see either the complete graph or the fully empty graph, right? So it's a density version of Ramsey. So if you can construct two source extractors, then you get Ramsey graphs there. You get bipartite Ramsey graphs, and if you take the two cover of this graph, you get a normal Ramsey graph. Alright, so now let's come to explicit constructions. So constructing two source extractors was raised in the 80s in computer science. And what's known as, so the paper which raised it by Shore and Goldrick, they showed that if you give me two sources, each containing an entropy greater than half, greater than n over 2, then there's an explicit two source extractor. And the extractor is very easy to define. It's just you treat this as a vector in F2 to the n, this as a vector in F2 to the n, and just take the inner product of them. That works for entropy greater than n over 2. Right? But as you have seen, probabilistically, there exists extractors for entropy log n. Right? So there's a huge gap. And after 20 years, John Bourgain used heavy hammers from additive combinatorics to get it down from 0.5n to 0.4999n. But it was considered a it is a breakthrough because of the kind of ideas that he used. And the main result I'm talking about is joint work with David Zuckerman, where we give a two-source extractor for entropy log to the 75n, and it runs in polynomial in a time. Alright, so that's the result. And in terms of Ramsey graphs, well, this has a longer history. This is by no means a complete reference to all the works that has been done. So existentially, I just showed 2 log n Ramsey graphs to exist. Various works using very different techniques from combinatorics or computer science came up to this bound of 2 power square root log n, right? 2 power square root log n. In the breakthrough work, these guys got to 2 power log n to the little of 1. If you really want to know what this is, then this is this thing. It's 2 power log n power 0.99. And our work directly implies Ramsey graphs with 2 power log n power c, where c is 75. Right? And currently pushing more extractor techniques. The current bound is log n power a lot of log times. And it's hopeful that we'll get to polylog n soon. So some ideas of our explicit construction. Ingradient. So seeded extractors come from zero randomness, from extractors. Non-malleable extractors, these things actually arise in cryptography, in a problem called privacy amplification, which is a really neat problem in cryptography. And finally, the third ingredient is resilient functions, which come up in distributed computing. And we'll mix these things together, two-source extractor. And a construction by picture is this. If this makes sense to you, then I'm sure you can come up with the proof. So the high-level idea is this. Take your two sources, x and y. So we get a sample from x, a sample from y. We use some things here, non-malleable extractors and samplers, to transform it into a single source. And we forget about that we have two sources, x and y. And this single source is very simple. It's this bit fixing source which I was talking about. So it's a source on n bits, it has few unknown coordinates which are uniform and independent, right? And the remaining coordinates unfortunately depend on the values of these randomness, so you cannot do the parity. Right? So these are called non-oblivious bit fixing sources. And it turns out resilient functions, so you can apply some resilient function and use some other ideas to get a uniform bit of it. Alright, so I'll try to give you some flavor of what these objects are, and if you do not follow the whole proof overview, it's fine. Maybe a few definitions will stick in, which is good enough for this talk. So I'll define what seeded extractors are. So this was defined by Eshan and David Zuckerman, Eshan and David Zuckerman, and it's the following. So it's an extractor which takes this weak source X, out of which you're trying to extract randomness from, and now you're given this independent helper seed. Think of D as small, like log n, right? You're given log n bits of uniform randomness, and using Y, you're trying to extract randomness out of X. So you want that the output of the extractor on X comma Y condition on the variable Y to look uniform, because you don't want the extractor to cheat. Right? Extractor could just ignore X and output Y. So what this says is that even if someone knows Y, the output of the extractor should look uniform, which kind of translates into saying that the extractor is extracting randomness out of the variable X. And there are explicit constructions known by a long line of work where the seed length is optimal log n, and you get almost all of the entropy out of the source X. Right? You get 0.99 or even 1 minus liter of times. So these are pretty useful objects. And here's an equivalent way of thinking about this. So you have this function extractor which is on 2 inputs. Let's try to define capital D, which is 2 power D. So think of D as log n, right? So it's a seed which is of length log n. So there are, if you cycle over seeds, there are poly n such functions, right? 2 to the log n, 2 to the order log n. So for each fixing of the seed, define this function fy, right? So now this function fy just takes the sample from X, right? That's the only input. And the property that this ext is an extractor, it's a strong seeded extractor, equivalently translates into saying that there is a large subset S of seeds, so 0.99 capital D, right? A large subset of seeds, such that if you apply the corresponding function on the source X, the output is actually close to uniform. And the translation is just using Markov's inequality, so it's simple. Well, I just want you to be careful because the set S has to depend on the source X, right? If it did not depend, then you choose one good seed that works for every source and you get a single one source extractor, which is not possible, right? We saw a contradiction that there does not exist one source extractor. So for every weak source X, there's a nice subset of seeds such that if you fix that seed, look at the output of the extractor from this source, you get uniformness. Right? This is clear. And I'll define what T non-malleable extractors are. These come up in cryptography. I'll not define it in the way it actually arises. So here is an equivalent way of thinking about non-malleable extractors, which just generalizes what we saw in the previous slide. It says that again it's a generalization of seeded extractors. It takes a source X and a seed Y, and now what we need is the stronger property that there is a large subset of seeds such that if you pick any T distinct seeds from your set S, then the joint distribution should look uniform. Right? So if T equals to 1, this is exactly the seeded extractor. Right? So there is a large subset of seeds such that the output of the extractor by fixing the seed is uniform. T non-malleable says that there is, so for every T seeds from your 9 good set S, the output is jointly uniform. And it turns out from a previous work of mine that you can actually construct such non-malleable extractors with log n seed length and for entropy log n. Okay. And the final ingredient is resilient functions, which comes up in this nice, in distributed computing from this collective coin flipping problem, which is the following. So suppose you have n players, and each of them have access to their own randomness, right? Own private randomness. There are n players, they are trying to flip a coin collectively. They probably do not trust each other. So what they do is, well, they flip their coin and send it to a trusted party, someone who applies a pre-decided function f, a Boolean function, on the n bits and outputs the bit, right? And the goal is to output an unbiased bit. Well, if everyone is honest, then the trusted party could just take the parity of the bits and output the parity, right? And the problem is not so interesting. So the malicious setting is the following: that there is a malicious coalition of players sitting here who do the following. They wait for the other guys to flip their coins, look at what they flipped, and then send in bits without even flipping their coin, right? Adversarial bits. Right, so they adaptively send their bits after seeing the coin flips of the other players. And you kind of, so if this malicious coalition is Q, you define the influence of Q to the probability that they can actually change the outcome of the function, right? So it's the probability that the output of the function f can be changed after the good players flip their coins, right? So if the good players flip their coins, those bits are fixed, and suppose the function f is already determined by those bits, and it does not help them to be adaptive, right? So it's the probability that they can still change the bits. The probability is over the flips of the good players' coins, right? Is this clear? And a resilient function is one which is one where small enough subsets do not have large influence on your function. So here is a very simple resilient function when f is a constant. And if f is constant, no set of players can change its value. But it's not so interesting. You want the output of f to look uniform, right? When all of them send you actually uniform bits, right? So the bias of f has to be 1/2. So again, you have this source x where the bits in Q are unfixed, the other bits are sampled uniformly, and the probability that f of x is not fixed is the influence of Q on f. And a Q, epsilon resilient function is such that for every coalition of size at most Q, the influence of Q on f is at most epsilon. And you want to construct such functions. And parity is a terrible example of a resilient function because even one unfixed bit can change the value of parity. So any guesses for a good, unbiased, resilient function? Majority, right? So majority is a good resilient function for anything slightly less than root n. You can use central limit theorem or tail box to show this. And the claim is that resilient functions are extractors for this source that we are reducing. So let's define what a bit fixing source is in the non-oblivious setting. Here, the bits here are sampled from some nice distribution D, and the remaining bits are correspond to the coalition, bad coalition, and these bits depend arbitrarily on the value of these bits. And if your function f is a resilient function, then it's easy to see that the output of the function on this distribution x is actually close to 1/2 if f is actually unbiased, right? Because if f is unbiased, then the probability that its bias changes under this distribution is the amount of influence that your coalition has. And if your coalition cannot change, does not have too much influence, then the bias remains almost close to being uniform. Right, so kind of we have seen this. So let's start out with the first part. So here is a simple letter. So we know that we have good seeded extractors, right? So let's start out by just using these. So let X be one of, so we have two independent sources with us. We are trying to construct a two-source extractor. Let's start out with taking the first independent source, getting a sample from it. And the idea is, take a good seeded extractor. The seed length D is log n, right? So you can actually brute force over the seeds. You don't need, someone to provide you with log n uniform bits. You can just run over all the n possibilities of the seed, right? So you take a good seeded extractor, take your sample, and just run over it. And what we have seen is that most seeds are actually good, right? So this capital S, this large set S, was that, if you take any seed from here, then the output of the extractor, so the extractor is just outputting one bit, right? The seeded extractor. So for every good seed, the output is actually uniform. So you have this string of poly n length, such that 0.99 fraction or even a larger fraction is actually uniform. Well, it seems there's a lot of uniform bits here, but unfortunately we do not know what the uniform bit is. So maybe a neighborhood would be just taking majority of these bits, but it's not clear because the uniform bits, individually they're uniform, but we do not know across each other how they're related. So the idea is to take a non-malleable extractor now and doing the same thing, right? And we have seen that the non-malleable extractor, if it's T non-malleable, then it follows that there's a large subset of seeds, such that if you pick any T seeds from that, then the joint distribution is independent, right? So now, if you produce a string, then there's a large fraction of seeds such that if you look at any T of them, then they're independent and uniform. But T is small, T is like log n, right? So the number of bits in this Z prime is poly n, and 0.99 fraction of these coordinates have the property that if you look at any poly log n of them, they're independent. And now probably the idea is to again apply majority. And it turns out that if the fraction of bad bits were actually less than root n of the length of Z prime, since majority is a resilient function, and it's actually resilient in this weak sense where it's not all the good players are not independent, but k-wise, t-wise independent, majority actually works. So we would actually get an extractor. But it turns out that the number of bad bits is much greater than the length of the string. It's actually d power 0.9. It's much larger. And this is not surprising because we have just used one source till now, right? And it's not possible to get an extractor using one source. Well, the idea is to compress using the second source to a pseudo-random subset. And somehow this compression gets us in a good shape. It's slightly technical, so I'll skip this. So the second source just comes in to compress the first source. So we take the first source, take a non-malleable extractor, run over all the seeds to get a long string, and sort of subsample from this string using the second source. Alright, so let's assume we have done that and we are through from our first step. So what we are left with is this new source Z, which we have constructed from the two sources, which has the following property, that the malicious coordinates are of size n to the n power 0.99. The remaining players are t-wise independent, where t is log n, right? What t-wise independence means is that if you look at any t coordinates, then their joint distribution is uniform, right? But t-wise independence is pretty far from actual independence. And the idea now is to apply a resilient function which is resilient to coalitions of this size and get a uniform bit out. I have 5 minutes.
Yeah.
Yeah. Okay, so it turns out that if the resilient function that you're constructing has a few properties, then in fact it's easier to solve you can reduce it to solving an easier problem where you can pretend that these bits, which were actually t-wise independent, so any t of them were uniform, you can just analyze this resilient function, assuming that they're actually all of them are independent. This is weird because the length of the string z is poly n, right? So if actually all of them were independent, the entropy of z is much greater than n. But we started out with two sources with entropy k, which is close to log n. So it has to be something special about the resilient function. And I'll skip over this. So so it turns out the following, that if the resilient function that you're constructing is actually a small depth circuit, right? A circuit is where you have gates which are AND, OR, and NOT gates. So it's a circuit of polynomial size. It's of constant depth, right? The depth is from the root to the bottom gate. It's of polynomial size. It's constant depth, and it computes a monotone function. If you can satisfy all these three properties, then it's enough to analyze it in the simpler setting where the good players actually have access to uniformness. And it turns out, so now we come to this problem of constructing a resilient function, and it turns out that in 1990, Aitai and Lineal came up with a probabilistic construction of such resilient functions. What they said is, well, there's this function tribes, which is very easy to describe. It's OR of ANDs, and each AND is on disjoint variables. So you can think of each AND being of an AND of a tribe, right? And this function evaluates to 1 when if there is a tribe which unanimously says 1. Right? So that's the tribes function. And if you partition n in any way, then you can construct a tribe out of it. Right? You partition it, then you take an AND of each of these guys and take them out. So what Aitai and Lineal said was construct this function, which is an AND. There's another top layer of AND of n random tribes, right? A random tribe is by a random partition. So you construct a tribe by a random partition, and then take an AND of all these guys, and also negate some things randomly. If you do that, then they showed that with non-negligible property, there is probability, there is some function sitting in there which is a resilient function. In fact, the resilience, so it's on n bits, and the resilience is actually n over log squared. So it's much better than majority, which is square root n, right? So there exist such functions. And if you go over the probability space, again, it will take you exponential time, which is not good enough for us. Plus, these are not monotone, so it's not good enough. And we show that there is this pseudo-random collection of partitions. So partitions correspond to tribes in the usual way, with certain pseudo-random properties. That any small subset has small intersection with these partitions. And the partitions are pairwise pseudo-random in the sense there is less intersection between the blocks of the partitions. If you can construct such partitions, and for each partition construct a tribe, take AND of the tribes, no need to negate, then you can actually construct a resilient function with resilience n to the 0.99, which is enough for us. And it turns out to construct such partitions, again we use extractors. And I'll conclude my talk with saying that we have covered everything, and answer any questions.
Is there anything known if you can use more than 2 extractors? Or
2 sources? Yeah. Actually, for 3 sources, it's same. You can do it for login. And this was known from 2013.
Can you use less than log n with more than two sources?
I mean, there's some dependence on t, so yeah, for constant you cannot go into
I have a question that's sort of maybe it reveals my confusion about the notion of one random bit. So if I want to test that I have one random bit, presumably I have to compute many times one random bit and do some comparison. And so effectively I'm computing a sequence. So is there a real underlying difference between computing one random bit and computing a sequence of bits that are random among themselves?
So you're kind of assuming you can independently sample a lot of types of this, right?
But what does that mean? I mean, each time you have to pick a seed, right, in order to do that. And the process of picking the seed is clearly fundamental to the algorithms that you're describing. And so now if I repeatedly pick seeds, how do I know whether I've done so independently?
I think that's an offline question.
You can ask the question that sort of, he makes the assumption that the string he starts with are the two strings are identical. And I guess in some way you don't see a way to test that hypothesis either. How do you know it has entropy? Like maybe it has no entropy. I don't know. Do we have I don't know.
Are there quantum ways of certifying randomness?
So maybe this is the same question, but what are the assumptions on your seeds? What exactly are you assuming about your seed? That it's generated by a Markov chain, like the bone model, is that? Are you assuming that?
It has entropy. It's an untestable thing.
Yeah,
It
it
has
has an
entropy.
entropy, but that doesn't make sense unless you can integrate it.
But then it really does. I don't know. Okay, I like to answer.
Can you repeatedly sample some source that gives you seeds?
Right, so I think the basic question is, given a source X, how do you know it has entropy K? Right, that's the question. I think there are quantum ways of certifying. Is there a quantum expert in the crowd? I think there's some, under some cryptographic assumptions, I think you can actually certify randomness.
What is a source? Is it something you can repeatedly sample? And it gives you some elements of
Just
an alphabet
Yeah, sure.
with according to some distribution, which could be correlated. Is that?
Yeah, that's
Okay, so what do you assume about that source? What are the basic assumptions about that source?
right. So I think the model. So yeah, there are various assumptions, right? You can assume, say, it's a small space algorithm, or you can assume it's a Markov chain. So there are various assumptions, and I think what was done so this was a lot, thought a lot in the 80s, and I think they sort of abstracted it out and said, well, let's assume some entropy in the process. So actually, if you assume, your source is generated by an algorithm with limited space, you don't even need two sources. You don't need independence. You can try to directly extract.
You could generate the seeds independently, then you can just, you have this log, whatever alphabet, you just repeat it as many times as you want and estimate the mean and go to that. And you can't do that. If you could generate the seeds independently.
If you could do it in this.
Isn't your assumption is that if you can repeat this as the two sources, is that no matter what the previous run was, the next run, you again have mean entropy K. That is, no matter what happened the previous 18 times, the 19 times the probability that you output a particular string, like all zeros or whatnot,
Okay.
cannot exceed 2 to the minus
Okay,
k.
so it's a non-deterministic thing. You have this large collection of distributions of min-entropy k, and then every sample can be one of those chosen non-deterministically, and you don't know what it is.
Yes,
That's
the
the
right
yes,
way to think
that's
about
a
it?
nice way to
That's the-
put it.
Okay. That's what I wanted to know.
So, in addition to two sources, if you can you sort of combine this now with the seeded, like if there was an additional seed which was good, there's some sense of like a trade-off between.
I mean, if you have some seed, then you can just ignore one of the sources.
But you need a minimum seed.
Right? So you're saying probably, yeah, I think you can.
But I was wondering, could you sort of trade off between the amount of entropy you need in your source versus the pure source?
Right. Yeah. Yeah, there's some work there. Yeah, it's in the parameters like.
Okay, so there were lots of cool deep questions. Luckily, we have a whole reception next door, I hope, hopefully. So these are wonderful for further questions. Eshan hopefully will be over in the other room and you can ask him arbitrary number of different or whatever food is over there. So thank you, Eshan.
Hey. What kind of class did you take? A class? I'm doing a rhythms.
I've never seen it
Is that a lot of, is that a big workload?
It's manageable. I can also do research. So it's okay.